In this video I want to provide a reminder about calculating the area between curves using definite integrals, and really what we're aiming to do is to sort of extend this to situations where we can use our new integration techniques that we've been learning. So first of all, just a quick reminder about how we can use definite integrals. So let's say we've got two functions here. This one here can be y equals f of x, and this one here is y equals g of x. And then between two values of x, x equals a and x equals b, we want to calculate the area that is generated between those two curves. So that's the area there that we're wanting to calculate. So hopefully we might recall from sort of maths methods that really what we're doing here is we're saying, well, if we could calculate the area from sort of the upper curve, y equals f of x, and the area between that and the x-axis, which would look like that. So let's say the area is going to be that area there. And from that we could subtract the area which is just under the lower curve, so this bit down here between that lower curve and the x-axis. If we were to subtract the second area from the first one, then we'd be left with the area that we're interested in. So that would be take away the region between a and b under the curve g of x dx. And that would leave us, like I say, with the area that we're interested in, that area there. So we could express that as just one single integral and say that's the region from a to b of f of x minus g of x with respect to x. And that should work fine for us. We just need to make sure that we've got the sort of upper curve first minus the area under the lower curve, so sort of have these in the right order with the curve that's uppermost minus the curve that's below it. If our curves cross over at some point in the region that we're talking about, then we need to make sure that we've taken that into account. So let's see if we can draw maybe a curve like this here. Say that's f of x, and then let's have another curve, or maybe a straight line here where that's g of x. And I haven't made them cross over again, have I? Let's try that again. See if I can make my curves actually cross over twice. I may not have quite. Oh, there we go. They're just crossing over there. So let's say that's g of x. And so I've got two different areas that I want to calculate here. I've got that area there and this area up here. So let's say the first point where they intersect has the x-coordinate a, the next point is b, and this last point over here is x equals c. So what we can see is that there's one section where g of x is sort of above f of x, and then there's another section where f of x is above g of x. So I need to calculate my area with two integrals there. So between a and b, do that again, between a and b, g of x is the sort of upper curve or above f of x there. So in that bit there, I'd calculate the area that way. And then for the second part, between x equals b and x equals c, f of x is the upper curve at that point. So that's how I'd calculate the area between those two curves for both those sections. So let's consider a specific example now. We've got let f of x be the function x squared minus 4. We want to sketch the graphs of that and also 16 over f of x on the same set of axes. Find the area of the region bounded by the two graphs and the lines x equals 1 and x equals negative 1. Should have said over here that obviously, like finding the area under the curve, all of this works where these functions are continuous between those 2 points. If we've got gaps or breaks where the function's discontinuous, then obviously we can't find the area in those situations. So let's try this one here. let's sketch x squared minus 4. Well, that's a parabola which has shifted 4 units down, isn't it? So it might look something like this here. So that's, well, where's our y-axis? Just about here, maybe. We'll say that's close enough. So that's going to be positive 2 and negative 2, and that's going to be negative 4 there, isn't it? It's going to be the x-intercept because it's been shifted down. So if we're now sketching the graph of 16 over f of x, well, wherever f of x has a 0, any constant divided by f of x is going to be discontinuous, isn't it? So we're going to have some asymptotes here for our function 16 over f of x, and 16 divided by negative 4 is also negative 4. So let me maybe just remove that there, get it out of the way. So let's say that's negative 4. So 16 divided by negative 4 is also negative 4. So this one's actually going to be shaped sort of the other way. Oh, that's a pretty bad curve there, isn't it? Let's try that again. Something like that. So there's y equals 16 over x squared minus 4. Now it does also then have other branches up in this part here, so it continues up here and here. That won't be too important for us because we're only interested between x equals negative 1 and positive 1. So I mean, all of this, I suppose, if this was tech active, would be quite a lot easier because we could just sketch this with our graphics calculator. But even without our graphics calculator, it's not too hard to work out some of those things. So negative 1 and positive 1. So between those two values there, that's the area that we're trying to work out. So because these functions are both symmetrical, we could sort of just work out, you know, from 0 to 1, we could just work out one side of this and then double it. So we could work out that and then double it to get both. But we could also take the integral from negative 1 to positive 1. And throughout that domain there, negative 1 to positive 1, the function x squared minus 4 is above the other function there, isn't it? So the area is going to be equal to the integral from negative 1 to 1 of x squared take 4 minus 16 over x squared take 4. So looking at that integral, well, these parts here are going to be easy enough to integrate. What about integrating 16 over x squared take 4? Well, it looks a little bit like maybe one of our inverse trig ones, but it doesn't have a square root over the x squared take 4, and it's not x squared plus 4, so it won't be an inverse tan, and because there's no square root, it won't be an inverse cos or an inverse sine. So I think actually what we're going to use for this one probably is just going to be partial fractions. So if we let 16 over x squared take 4 equal a over x minus 2, wouldn't it be? Not x minus 4, x minus 2, and b over x plus 2. Therefore, the numerator on that side would be equal to the numerator on this side. Which would be something like that. If we let x equal 2, then what are we going to get? 16 equals 4a. And if we let x equal negative 2, then we would get 16 equals minus 4b, so I think we'd get b equals negative 4. So our area is going to be equal to this here. What have we got? X squared minus 4. And then it's going to be, now we're taking away, aren't we? So let's be a bit careful with our signs here. We're taking away all of that. So if we're taking away this where A is a positive and B is a negative, it's going to be taking away 4 over x minus 2 minus negative, or rather plus negative, so minus 4 over x plus 2. So what is all of that? X cubed over 3 minus 4x. And then here I guess we could sort of switch these around to make that one a plus 4 over x plus 2, and then a minus 4 over x take 2. So that would be plus ln of x plus 2 minus ln of x take 2 between negative 1 and 1. So we could actually combine those two logs using our log laws into a single log, isn't it? It would be the natural log of x plus 2 over x minus 2. I don't have sort of heaps of room here, but let's go substituting in positive 1 is going to give us this, and then we're going to have the natural log of, so 1 plus 2 is going to be 3, and then 1 minus 2, so it's going to be negative 1. Take away negative 1/3 plus 4 plus natural log of, so subbing in negative 1, that's going to give us positive 1 there, negative 3 there. And just as I come to almost evaluate this, I can see that I've left something out back here, haven't I? So both of these had a numerator of 4, so I should have a 4 in front of both of those. Can I squeeze that in here? Let's see whether I can just squeeze those in. So it's going to be a plus there and a minus there. So this here is going to be plus and minus there. So I think, is that right there? So what do we get when we look at all this? We got 1/3 plus 1/3 is 2/3. We're going to have take away 8, and then all together we're going to have a 4 ln 3, and that one's going to be plus 4 ln 1/3. So we're almost there. Hang on, let me correct that again. Isn't it? That one should be a plus. It can't be minus in one and plus in the other. So that makes that one there a minus. And then I guess what we could do is recognize that if we sort of raise that to the power of negative 1, then, or yeah, if we take this negative 1 here and make it the power there, then it actually becomes plus 4 ln 3. So altogether we've got 8 ln 3. We don't really need that anymore, do we? 8 ln 3. And what's that? 8 is 24, so minus 22 over 3. So 8 ln 3 minus 22 over 3. Then you could grab your calculator and just check that that does actually give you a, I guess we're expecting a small positive value for that one there.